Our next speaker is Vincent Gramoli from Sydney and Data61, which I guess is a company. And we'll talk about ICOs.
Thank you. The pointer doesn't work, so I'm just going to put it aside. Sorry for that. Thank you for the introduction. Actually, Data61 CSIRO is not a company. I mean, it's a government-backed institution. So it's the equivalent of the CNRS. So it's an international national institution, which stands for Commonwealth Science Industry Research Organization. So the work I'm going to talk about today is a collaboration with someone from the School of Business that we did we started doing that back in 2017. And that was an interesting collaboration because at that time we really wanted to understand Ethereum. And so we were asking people around who were knowledgeable in this space, and we ended up talking to economics, people in economics. And this is essentially the work done by Michael Spain, who is the student in this list of authors, and Sean Foley is from the School of Business. I also work at Data61 in addition to University of Sydney. So the context of the talk is about initial coin offering. So we were interested in ICOs at that time, and we were asking ourselves the question, it looks like it's very popular. ICOs are very popular. And again, that was back in 2017 when we started. And we were wondering whether it could be the case that some people with more coins or more money could essentially get access to tokens that the poorest individuals or the users with the least amount of coins could not get. And so an ICO at a high level is a method of raising funds through a blockchain system. Okay, so the blockchain is used as a tool for the ICO, where the buyer will essentially purchase tokens. In parentheses, I put security because there are a lot of tokens that are considered securities, which are assets with values that evolves over time in a speculative way. But of course, there are other types of tokens like utility tokens and so on. And this buyer will get access to this token at an agreed price from the seller. Okay. These ICOs facilitate individual participation in the sense that you don't need to be an accredited investor or a sophisticated investor to get access to these tokens. Essentially, people around the world can access that by just using a software running on their computer. And in 2017, hundreds of ICOs occurred on one blockchain, the Ethereum blockchain, because it features this concept of smart contract, which is like a more complex type of program that can accept transactions and will automate the terms of this contract. In particular, ICO raised $20 billion through 2017 and 2018. So let's talk a little bit about Ethereum, but I guess most of you are knowledgeable in the principles behind this blockchain technology. Ethereum was very popular because it offered for the first time this ability to implement smart contracts that can define ICOs, for example. And you can find the details in the yellow paper written by Gavin Wood. But essentially, the idea is that you have a miner, and a miner is like a server providing the Ethereum service to others that will maintain the blockchain that is represented here at the bottom in yellow. So this is the Ethereum blockchain, and here we will only talk about the Ethereum main chain. Okay, there are other instances of the same source code, Ethereum source code, but here we focus on the Ethereum main chain. And then you have a seller that will typically upload a smart contract by asking the miner to put it in a block of the blockchain. Later on, the smart contract will be included in the block if the miner is happy to do so, if he's incentivized to do so. And then later on, the buyer will have access to the smart contract by sending transaction that will invoke a function of the smart contract. Right? So here, the seller is the one that I indicated previously, is the one who will program the ICO. Okay, so he will write the smart contract that defines the terms of this ICO. It will be uploaded to the Ethereum blockchain, and then later on, the buyer will have access to these tokens that are sold through this particular smart contract by issuing a transaction. But of course, there can be multiple buyers, especially if they are all interested in getting the tokens at the same time, there will be some competition. So there's an interesting notion that was introduced as part of Ethereum, which is the notion of gas. That is important to talk about in this slide. The gas is a metric that can be used to represent the computational complexity of executing a smart contract or the function of a smart contract. There are two interesting values that we will use in this talk: the gas limit, which is the maximum amount of gas spent during the transaction, when the transaction executes, and the gas price, which is the price that the sender is willing to offer to the miner. So it's a bit confusing. The sender here refers to, in this particular example, the buyer, right? The buyer willing to buy tokens is happy to give a certain price associated with his transaction to incentivize the miner to put the transaction into a block. Because he knows that if he can get access to the tokens before others, or if he knows that the tokens are in limited supply, then he has a higher chance of getting access to these tokens, if the fees is higher, in theory. Okay, so this gas price and gas limit can be used to define a fee that the miner will receive. The fee is simply the product of the gas price set by the buyer or the sender of the transaction times the gas used by the transaction. It's normalized with 10 to the power of 18 just because the gas is expressed in the Wei unit and the fee is expressed in Ether. Okay, so there is a relation between Wei and Ether following this multiplicative factor. So essentially the fee here is what the miner will get by including this transaction. But more generally, as you can see at the bottom, the miner will get a reward not only for including the transaction, but also for creating the block. So in the end, the reward given to the miner for a particular block B that he has created is 5 Ether plus the sum of the fees of all the transactions in this block. Okay? So you can see that there is supposedly, or we can imagine that there is an incentive for miners to include transactions where the fee will be high, right? Because the miner will get more Ether, or ETH. So the problem we're focusing on today relates to a paper by Moser and Bohme that was published in 2015, where they observed that in Bitcoin, the higher the fee users are willing to pay for a transaction, the more likely or the faster their transaction will be accepted. So if you place this in the context of ICOs, where somehow the tokens are in limited supplies or they are offered for a limited amount of time, then you can imagine that you can get access to these tokens if the same rule that applies to Bitcoin also applies to Ethereum by increasing the fee of your transaction. And also we noticed in 2017 that most of the transaction of a 3-month study of Ethereum indicated that most of the transaction would take more than 3 minutes to be included in Ethereum. So it's also indicate another thing that you can do, where essentially you know that someone has submitted a transaction because your peer received this transaction through the network. And potentially you have 3 minutes to get access to the same thing that this transaction are trying to access, right? So essentially, if you can increase the transaction fee, then you can potentially front-run another transaction because you have 3 minutes to try to have your transaction included faster than another transaction that you have seen. So it could lead to potential problems. Especially, we can imagine that it could be a fairness issue where the wealthiest people would essentially get all the resources, like all the tokens out of the system before any person with a low transaction fee would get access to some. So the question we ask ourselves is, can buyers purchase tokens before others by increasing their transaction fee? It would make sense, right? If the same thing applies, if the same observation that was noticed in Bitcoin also applies to Ethereum. So what we did is we took a look at the popular ICO, which is the Basic Attention Token ICO. This ICO was popular in the sense that it raised $35 million in less than 30 seconds in May 2017. And what we did is we collected more than 10,000 blocks around the period of the ICOs, essentially 1 day before and 1 day after the ICO. There were 5,000 blocks before the BAT ICO and 5,000 after the BAT ICO that we collected. The data were obtained from the Etherchain public API, so it's publicly available. And so what we did is we plotted so on the x-axis here you have the time that increases, but essentially this is indicating the block indexes. Okay, so these are block numbers essentially, and the block number of course increases as time elapses. And on the y-axis you have the total block fee. Okay, so that's the fee within each block. So essentially each individual blue dot that you have on this graph is one block that represent by its height its block fee. Yes.
Should you not plot the average fee per transaction in a block? Because the number of transactions may be varying. Maybe
Yeah.
those are empty blocks before, and these ones are full.
So this is the entire fee within one block.
Yeah. So
Yeah.
it's meaningless. You have to divide it by the number of transactions, right?
Yeah, so we have all the results on the number of transactions. I will go to that later. So it's just, this is just the fee per block, okay? So first observation is that we look at the fee per block and what we see is a peak. So there is something happening. We don't know what it is exactly. We don't know how many transactions were there, okay? So, but we see that during the block number 3,798,640 and the two following blocks, that was the time of the BAT ICO. We know that, okay? It occurred at these three blocks. So what we can see is that there is somehow an increase in the block fees at this time, around this ICO, okay? That's the first rough observation that we do. Okay, so we went a bit further into this study and we tried to see why we had this peak. And we computed the average, some metrics before and after the ICO compared to the three blocks of the BAT ICO. Okay, so what you can see here is that we listed the total block fee. Okay, we also listed the total block size and the number of transactions per block. So that's an additional information, and the gas used per block. Okay, so it's a little bit more information in this table than in the previous graph. But what we did is we isolated this peak by saying, okay, what happened during the three blocks of the ICO that you can see in the three last columns, and we compare that to what happened on average outside the ICO, which is represented in the second column, if you want. So essentially the blocks are in the three last columns, and the second column indicates the average outside the ICO. So what we can immediately see is that there is a big difference in block fee. That's not a surprise. And, but essentially the fee were 300 times higher on average during the ICO than outside the ICO, okay? Which is significant. So it confirms our hypothesis that people willing to purchase token will be willing to put a higher transaction fee. They will be willing to give more coins to the miner, and supposedly to have their transaction accepted faster and to make sure that they will get access to some tokens. There were around 50% more transaction in the first ICO block than in the non-ICO blocks also. So we can see that there was a demand increasing during the time of the ICO. Okay, we also looked at, on this graph, the gas that was used during this period. And again, we retrieve a peak at the moment of the ICO, indicated by this arrow. And what we noticed is that essentially the gas used was close to the gas limit that was provided in Ethereum at that time. So essentially, using this evaluation just for the BAT ICO that was quite popular, we confirmed that users are happy to pay a higher fee during the ICO. This is profitable to the miners that don't have much additional work to do, but essentially they will get a much higher fee, like 300 times higher during the ICO period. This could potentially lead to a lack of fairness for the buyers in the sense that if you have you cannot afford a high transaction fee, then you may not get access to any of the token. especially given that the ICO lasted for 30 seconds, if you remember. So it's quite short period of time. So what we wanted to do is to go a little bit further and see whether the transaction latency would be affected. Okay? Okay, so what we did is we expanded the study. We looked at 19 other ICOs that were, we essentially focused on a period of time, and within this period of time, there were 19 ICOs. What we want to capture here is the time taken between the invocation of a transaction and the commit time of a transaction. Of course, the notion of commit in Ethereum is a bit blurry in the sense that transaction can be reordered, and if messages are taking a long time to go across the network, then the transaction that has been included in the block may get discarded later on or put back in a mempool because it was not part of the canonical chain. So we had to approximate this notion of latency. Okay? We couldn't get the clear latency of a transaction. The timestamp when a transaction is broadcast cannot be obtained, right? We couldn't have access to all the clients of the Ethereum main chain, for example. So what we did is we used miners that were receiving transaction, and these miners were modified so that they would timestamp the time where they would receive the transaction for the first time. And using this information, we computed a timestamp that we call T received, which is the earliest among all the miners that were modified. It's the earliest time when they received the transaction. We compute the latency as the difference between the timestamp, the block, when the block was created with transaction T, and this earliest T received timestamp. Okay, so essentially the latency is simply the time, the difference between the time a transaction is included in a block minus the time it was received by the earliest time it was received by one of our miners. This gives an approximation given that clocks are sufficiently synchronized. Of course, this is again an approximation because we cannot ensure that the clocks are synchronized, so the timestamp may not be exactly the same. Okay, so it was measured. This latency was measured on all the transactions that we collected during this period of time, which was a period of time of 42 days in 2017. We had more than 60 million transactions. There were 19 ICOs at that time, including Tezos, for example, one that is quite popular. And we measured, this measurement were collected in different places. And so we had to remove some of the duplicates T timestamp received, for example, by choosing the earliest among all.
So this was in 24 days you had 19 ICOs?
Yes.
This seems like very active, and I'm not sure it's going to be like that forever.
No, I think it's no longer the case. So again, yeah, we were, 2017 was a particular year for ICOs. It was very popular to use Ethereum to do ICOs. What we noticed is these 19 ICOs raised cumulatively $700 million. So that's quite a big number. Yeah, so I guess now it's...
So to what extent is, this is very interesting as forensic, but what's the relevance of this period for the world from now on?
Yeah, that's a good question. I think it doesn't apply now, essentially, and that's part of future work, is that we need to redo this study with more recent data. What I'm going to talk about next is the time, essentially the, okay, thank you.
Okay, sorry.
No, so essentially what happened is that Ethereum modified the gas price, and I will explain how it impacted the the way wealthier individuals could get access to tokens. Okay, so the latency distribution, we also collected some, or did some statistics about the distribution of the latency by plotting the percentiles. And what we could see is that there were some transactions that would take a very long time to be included, following our latency definition. The median transaction latency observed was around 22.1 seconds. The average block time for this period was 17.6. seconds, okay, just the block time, so it's the interval between two consecutive block creation. This means that 2 blocks are created before most transaction would get included. Okay, so a transaction will take more than a block creation period to be included. Okay, we plotted the latency, and again, we can see that there is a heavy tail, or there are some transactions that will take a very long time to be included. And we computed the correlation between the fee associated with the transaction and the time it will take for this transaction to be included. Again, with respect to our latency definition. This correlation is negative, which confirms the fact that there is an inversely correlated correlation between the fee and the transaction latency. It makes sense, but it also what we noticed is that this correlation is extremely low. And this indicated that there is not really a cause and consequence relation between these two things. So we investigated the maximum throughput that you can get out of Ethereum based on the the maximum gas that you have in the blocks, or that you had in the blocks at that time. And what we observe is that in June 29th, the miners began consistently voting to increase the gas limit. So that was during the period that we studied. And as a result of voting for a higher gas limit, what happened is that in Ethereum, the limit that you could, the limit of a block in terms of gas was increased. Okay, and it was increased by 43% on the 29th of June. And this had a huge impact on the capacity throughput of the Ethereum blockchain. So the throughput was increased as a response to this increase in the gas limit. If for example, we took the median transaction size in gas, and we observed that it was around 90,000 during our study, the average block interval time was 17.6 seconds, as I said. And so essentially, given the number of blocks you could create per second, and also the median transaction size in gas, then you could deduce some evaluation of the throughput you could have, like the maximum throughput you could have in Ethereum. Again, it's a rough estimate because it's based on the median transaction size. And we could see that essentially the throughput was increased due to the increase in the gas limit. And it turned out that this increase in the gas limit and also in the maximum capacity throughput of the Ethereum blockchain resulted in moving from this particular graph at the top to this graph at the bottom that indicates the relation between the fee, the transaction fee, and the latency of the same transaction. So you can see at the top graph that it's not always the case if you put a high fee with your transaction that your transaction will take a short period of time to be included in the blockchain, right? There might be some at the extreme right side of this x-axis on the top graph, you can still see some blue dots at the top that indicates that it took a long period of time, even though the price or the fee of the transaction was quite high. But then when the gas limit was increased, which resulted in an increase in the capacity throughput of the Ethereum blockchain, we can see that this relation was more visible in the sense that the fee would impact more the latency. Okay, this is what you can see on the bottom graph, where essentially if you put a higher fee, you would get a lower latency on average. Okay, so to conclude, we analyzed the Ethereum blockchain during these 20 ICOs. The buyers are happy to pay a significant fee to have access to tokens. That was the first observation. But surprisingly, the fee did not really help these buyers to get the token before the others. The demand and the offer were the predominant factor. So essentially at that time, Ethereum was so congested that the reason why people would get token was depending on the demand and the offer, like the amount of transactions that were submitted at some point in time, and also the maximum capacity throughput of the Ethereum blockchain. So that was a bit surprising when we did this study. But again, since then, the gas limit has increased. And so it resolved partially this problem. So of course the future work includes to look at more recent set of data, like in 2019, to see if it's still the case. Given that ICOs are less popular, maybe we can expect that by putting a higher fee with your transaction, you would have a higher chance of getting what you want in the Ethereum blockchain. Here are some references, and I come from Sydney, and So if you come down under, please come to the University of Sydney. Thank you.
So we had 2 questions, but there is time for a few questions. There.
Yeah, I was just wondering if when you're measuring whether or not paying fees increases the speed of getting a transaction processed, are you comparing a transaction that got processed in terms of whether it got processed quicker than another or whether it got processed at all? That is, are you accounting for the fact that some transactions might not have been processed?
Can you speak louder, sorry, or closer to the microphone?
Yeah, sorry. I'm just trying to understand if when you're looking for this effect about whether or not transactions were processed faster as a function of the fees that were paid.
Yep.
I'm wondering if you're looking sort of at like an intensive margin about whether or not some transactions were processed faster than others or whether some transactions were not processed at all.
Okay, so we didn't really look at whether transactions were not processed at all. There was this paper from 2017 where we looked at whether transaction would not be processed at all. It turns out that in Ethereum, even though your transaction is not included in a block, it may end up in an uncalled block. The result of that is if your block is discarded, is not part of the canonical chain, then your transaction will be put back into a mempool. And what will happen is that later on, eventually, especially if the demands start going down, then your transaction will be reproposed as part of a block, and eventually it will be included. What we noticed in the study in SRDS was that usually a transaction, during this period of the study, a transaction would be a part of 3, it would be included 3 times, so it would be part of 2 uncalled blocks maximum. So eventually your transaction will go through. There is no way you can abort it. There is no way you can cancel it when it's gone, when the miners receive it. What we were focusing on here is really the latency of the transaction, so the time it takes for your transaction to be processed.
So I would like to criticize this a little bit, particularly what you just said. So in reality, about 80% of all transactions submitted to the Ethereum blockchain, to the Ethereum network, will never make it to the blockchain. And the reason for that is precisely because of these things that people are competing for some resources. It's usually not as apparent in ICOs as it is in DEXs, the distributed exchanges, when people see some offer and they want to get on that offer first. What happens is the so-called gas price auction, when competing offers are submitted to the blockchain and they are replaced by transactions with the same nonce but with a higher fee.
Yep.
And the economics of these gas price auctions is the same as the so-called dollar auction, because the loser also pays. So eventually both transactions will be included in the blockchain, but one of them will just fail.
Yep.
Because it will not get the resource, because the previous one that did. And during this auction, a whole bunch of transactions will be submitted to the blockchain, but they will be replaced by same transaction offering a higher gas price. And actually that explains what you have observed, why some transactions, even though they pay a high gas price, are included fairly late. Because what miners do, miners obviously are observing these things. Miners are keenly aware of this happening in the mempool, and I think your study would benefit a lot from observing not only the blockchain but also the mempool, because most of the action actually happens in the mempool.
Yeah.
And what you will see is that if they notice that there's a gas price auction going on, of course they will hold off, because they're just waiting for these people to outbid each other, so that in the end the miner will get a much higher gas price. So they're actually letting these gas price auctions run, and they don't include the high gas price transactions because they expect them to go even further. And they, because of their economics, their game theoretic property is the same as the dollar auction, they actually reach crazy gas prices. Because the incremental value, the marginal increment in the gas price is still worth it, even though the whole gas price is completely outrageous. So I would like you to consider looking at what's going on in the mempool, because it's very interesting. And actually the resource to do that would be a website called frontrun.me, frontrun.me. They have collected a lot of mempool data and have analyzed it from this point of view. And also, on Ethereum, you can compensate miners outside of the gas price of your particular transaction. So you can actually bribe the miners through smart contracts. You could put smart contracts on the blockchain that would pay the miner extra if some outcome of the gas, for some outcome of a smart contract. And that is also happening. And miners can automatically detect that. They try to include certain transactions and they see how that affects their revenue. So miners are currently sophisticated enough to automatically detect if somebody is trying to bribe them and take that bribe. And with that, you can actually see strange things happening, like high fee transactions not included, and so on. So, what you have seen in the blockchain is just the tip of the iceberg.
Yeah, I'm not saying that it's a complete analysis of what we could observe, but to go back to the previous question, it's true that if you have transactions that are conflicting, then they may be discarded for good. So essentially what I said is not true in the sense that if you send a transaction and someone sends a transaction even later that conflicts with this transaction, it can be accepted before, which means that your transaction will never be accepted, right? So there are all sorts of conflicts that we didn't look at during the SRDS study, but for this particular work, yeah, that would be interesting to, as you suggested, to look at the mempool and maybe the smart contracts themselves to see how the miners are rewarded.